Happy Monday. We'll get started. All right. I haven't marked your test yet. You're not the only ones who are so, I know, come on. What have you been doing this whole time? I know, right? Not as bad as networking. Well, hopefully that's a course. I know I do feel bad about not having them back a week after, but it's been a crazy week. So, but I'm working on them, and you'll get an email as soon as they're finished. So, of course, you know the drill. All right, so what I want to do is just finish up our numeration systems. Yeah, bonus 1% per day. I'll see what I can do. Usually what happens if I've had to put off marking for a long time, then I feel really bad. And then I'm more generous when I'm marking. So usually that's what happens anyways. So it works out in your guys' favor typically. So anyways, or I'm like, I've forgotten all this stuff, whatever, who cares? Everyone seems okay with that. So, all right, so we'll finish our numeration systems. Yeah, that looks like numbers. Moving on. Pretty much. We're going to start by talking about the binary numeration system, and then we'll focus on moving between binary, octal, and hexadecimal numeration systems. And there's I'm going to say 2 shortcuts that I'll teach you moving between the 2, and then we'll be done with our numeration systems. As you probably are aware, of course, binary is really important in computer science. Because that's how we communicate with computers. And so first we'll start and we'll talk just about the binary numeration system. Binary numeration system. Okay. So in order to communicate with a computer, we as humans had to invent a number system that only requires zeros and ones, right? If you think about a computer, it's just a series of switches, on-off switches, right? So zeros is off, 1 is on, right? And you just flick these on and off, on and off. Beep, beep. Anybody home? So let's see here. In order to communicate with a computer, we had to invent a way. Here's my ESL coming out. Invent a way. I want to say invent a way. Invent a way of representing numbers and other symbols. Yeah, we had to invent a way. I want to do W's for both of them. I also have a hard time saying vacuum in a sentence, but I'm not going to try that. So representing numbers and other symbols in terms of on-off switches, right? Oh, I'm Swedish, so I speak Swedish. I did growing up, but then obviously we moved here. Hey. Yeah, so I can talk like this if you want me to, but it might be hard to follow. Okay, so we've got a series of on-off switches, and so binary was born, right? So when working in base 2, which is binary, I didn't study in Swedish, so I'm actually not very good at the terminology, like higher level math stuff in Swedish. Otherwise, I guess I could. I can figure it out. Take forever though. Yeah, the problem is when I get going on the accent, it's hard to stop. So, yoo-hoo, big summer blowout. Yeah, or at least at IKEA. So, I thought I had told you guys that, but I guess no. Maybe someone picked up on it, I don't know. So when working in base 2, which is binary, we only have zeros and ones as our symbols, right? So we know we only have 0 and 1 as our symbols. So 0 is kind of like an off switch, and 1 is on. So you go into the depths of our first computer, and it was just a series of kind of on-off switches. I don't know a lot about computers and that kind of stuff, obviously, but I do know that. So binary. Let's think about, and sort of as a review, I haven't done a review because we had a test last day, even though that was last week. But just as a quick sort of review, I want you to change 1110 base 2 to base 10. So this was a while ago, right? So if we're working in base 2, how I do it is I write these out a little bit lofty, 1, 1, 1, 0. And I'll use a different color here. 0 is times 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So this becomes, so this base 2, we know from before, even though if you're anything like me, as soon as I walk out of a test, I've forgotten everything that was on it. So I could just go in, know it, and then I walk out and everyone else is talking about, oh, what'd you get for this question? What'd you get? I have no idea. I don't even know what question was on there. I just did it. So 1 times 2 to the power of 3 plus 1 times 2 to the power of 2. And I'm going to scoot this over because I need some more space. I should have known that. 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. This is 1 times 8. Writing out everything here. Of course, you can just skip straight to here if you want to. But I just want to show you where everything is coming from because it's been a long time. So 1 times 8 plus 1 times 4 plus 1 times 2 plus 0. 8 plus 4 plus 2 plus 0 puts me at 14. So we were able to communicate the number 14 in binary, which if we're thinking about on-off switches, right? If we had a series of just 4 switches in a row, it would be on, off, and that would communicate the number 14. Right? So, going the other way, so remember if we have to change a decimal, so a base 10 number to base 2, then we can do repeated division. I think we landed on that being kind of a fan favorite, or at least it's my favorite, so that's what I'm using. So, because I think I'll need a little bit more space here, I'll scoot this up. Constantly scooting. There. Hey. So if I want you to change 47 to a binary numeral, I'll put it kind of way down here because I think I'll need quite a bit of room. Right, but what we do is we just divide it by 2 and keep going, keep track of those remainders. So 47 divided by 2, and here's where I always do a poor job stacking these, but 47 divided by 2, whoops, 47 divided by 2 is 23.5, so of course 23 goes here, and 23 times 2 is 46, so I have a remainder of 1. My only choices for the remainders are 0 and 1 when I'm working in base 2, so that's easy, right? 23 divided by 2 puts me at 11 with a remainder of 1. 11 divided by 2 puts me at 5 with a remainder of 1. 5 divided by 2 puts me at 2 with a remainder of 1. 2 divided by 2 is 1. With a remainder of 0, and finally, 0 with a remainder of 1. So close. 1 line away. Hopefully you can see there. We've got a little 0 on top with a remainder of 1. So what we can say then is that 47 base 10, I'll just emphasize that you don't have to put base 10, but sometimes it's hard to keep track, so it's nice to just write the 10. 47 base 10 is the same as 1, 0, 1, 2, 3, 4 ones, 1, 2, 3, 4 base 2. Okay. Now, I'm not really the one to teach you about bits and bytes, but maybe you've heard of them before and it'll just be a little review. If not, I'm sure it'll come up. So here we go. So each switch, so each on-off switch is called a bit. Okay? And a series of 8 bits makes a byte. Okay? So in a computer, each switch called a bit, which stands for, it's a kind of a, what's it called when you smush words together? Binary digit has been smushed together to bit. Bits. Portmanteau. Yeah, see, I don't know. I don't know. Portmanteau. IDK. But it's from binary digit. And the textbook has the B and the IT. Nice. Portmanteau. But couldn't it be the BI and then the T? Anyways, either way, it's bit. So in a computer, each switch, which is called a bit, represents a 1 or a 0. A 1 or a 0. And depending on whether it's on or off. Man, this is a run-on sentence. Depending on whether it is on or off. End of super weird sentence. Okay. So like I said, so here's a bit. Okay. And then a group of 8 switches makes a byte. So a group of 8 switches is lined up to form a byte. Is lined up to form a byte. Which means that now I have 8 on-off switches in a row, right? Which can only represent so much, but it represents quite a bit. So which can represent any number from 0, oops, any number from 0 to, and now just 8 ones in a row, right? That's maxing it out. And so of course 0 would be 8 zeros in a row. And then 8 ones in a row would be 1, 2, 3, 4, 5, 6, 7, 8 base 2. And if you go through and you do this conversion just like we did, right, from base 2 to base 10, well, then we would find that this is the same as 255 base 10. Okay. So that is obviously not everything that we need, right? So we do combinations of these things. So we're just going to tack them on. Okay. I'll just make a note here that here we have 8 bits is 1 byte. Bits and bytes. Okay. Okay. So we need more than that, right? We need more than 255 things, obviously. And so what they developed in the 60s is the Ascii Code. And so the Ascii Code is just code for everything that, every symbol that you might want to generate, or that a computer is able to generate, rather. So since we need to be able to represent more than just numerals, to be able to represent more than just numerals, okay, the ASCII ASCII which is just in case you're curious and you don't want to Google it, I don't know, is the American Standard Code for Information Exchange. Standard Code for Information Exchange. So the Ascii code, oops, ended my sentence. Another weird sentence coming at you. So I guess I should read my sentence, make sure it sort of makes sense. So since we need to be able to represent more than just numerals, the Ascii code has been the most commonly used. Has been the most commonly used. And what I want to do is I want to show you the table, which is come on, here. Just so just some ASCII code. Right. Oh, I wanted exchange. Interchange. No, I can't remember if I said exchange or interchange. Thank you. Good. Exchange, interchange. I'd say I'm still safe. Should be interchange though. So what was developed was an ASCII code of 32, for example, is a space. Okay, 33 is an exclamation mark. And so we can go through, of course, a capital letter has a different code than lowercase letters. Right, and so a capital A is 65, whereas a lowercase a is 97, right? And so everything that we generate, all the symbols that we need are attached to an ASCII code, and they're all going to be unique, of course, otherwise it makes it hard. So let's do a little example. What if we have to write the word cat, lowercase cat, in ASCII code? Okay, so if I want, give me a C. A C is a lowercase c, presumably 99, right? No reason for it not to be 99, even though we don't have the whole table. So I'm going to say 99, and a lowercase a is 97, and a lowercase t, I'm going to tell you, is 116. You could figure it out, but why? Okay. So here, what happens is that each of these three would be a different byte. Okay. Each of these three symbols would be different bytes. So what we can do is, okay, if we have this this ASCII code 99, what we can do is we can convert it to binary. And remember that a byte has 8 slots, right? And so what we can do is we can say, okay, well, if we have a symbol, CAT, for example, then we have the ASCII code, which was 99, 97, and 116. Then in binary, we would have, and I'm just going to tell you what it is. For the first one, 0, 1, 1, 0, 0, 0, 1, 1. Okay. So that's, of course, base 2 because it's binary, right? And let me just make sure that I have 8 here. 1, 2, 3, 4, 5, 6, 7, 8. Phew. So what would my byte look like? My byte is going to be on, off, on, off, on, off, on, off. In this case, it's going to be off, on, off, off, on, on. You might have missed an off. So off, on, off. Da, 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 da. Okay. So what you can do is, and I'll just give you the binary codes here and we'll just kind of start the byte. We're not going to finish them because I think it's pretty obvious, you know, 0 is off, 1 is on, and there's nothing that we really do with it. So 97, I'll give you the binary. Of course, you could go through and convert all these to base 2 using repeated division, right? 2 goes into 97, how many times? Then that goes, 2 goes into that, how many times with the remainder, and then figure out your binary. But here we go, 0, 1, 1, and then 1, 2, 3, 4, 1, 2, 3, 4, 1. So here, this is off, on, off. They'll start the same. Okay. 116, if you wanted to, and it might be a good exercise to be able to go through and just take base 10 into binary. 0, 1, 1, 1, 0, 1, 0, 0, which of course is off, on, off, doo, doo, doo. Okay. Okay. So then each of these bytes are stored at some address in your computer. So each of these bytes, oops, is stored at some location in the computer. It's in the computer. So stored in the computer. All you had to do is turn left. I haven't seen Zoolander 2, but Zoolander 1 was so good. I'll make an effort not to see it. Oh, that bad, huh? Maybe we're just a little bit older. A freak gasoline accident. A freak gasoline fight accident. Yeah. Okay. They're in the computer. Oh yeah, and that location, of course, is called its address. I keep losing my train of thought. I'm thinking of Zoolander. It needs to be at least 3 times as big. Is it 3 or 2 times? That's what we need to know today. So at some location in the computer called its address. So each address stores 1 byte of information. Okay. So for example, to store something like 3 cats, right? I guess it's not so much an example, right? But we would need 6 addresses, right? We would need the 3, the space, right? We need to generate that space, the C, the A, the T, and the S, right? And these are all lowercase. I guess it's an example. To store the phrase, I guess, 3 cats, we would need 6 addresses. And I'll just do 1, 2, 3, 4, 5, 6. Okay. I think that's enough about bits and bytes. Like I said, I am not the best person to teach you everything about it. I don't know very much about it, so obviously Ken will teach you all about it. Tell him I said so. I will teach you about binary arithmetic. That sounds like math. Now we're talking. Okay, so for binary arithmetic, and I'll underline it so you can find it later. Oops. Yep. All we need to know, well, we need to know how to add and multiply. So that's our arithmetic. So all we need is this. So if we're adding either 0 or 1 to 0 or 1, right? So here we have addition, and we could also do multiplication. Okay. And I'll set up the multiplication matrix as well. 0, 1, 0, 1. Okay. So just think about, okay, we're working in base 2. So whenever we hit anything greater than 1, we loop back, right? And we have to bump it out. So we write 2, for example, in binary. So 0 plus 0, if we go through 0 plus 0, well, that's 0. 0 plus 1 is 1, and 1 plus 0 is 1. The only pickle is that here, right, 1 plus 1 in base 2, right, 1 plus 1 is 2, so 2 in base 2 is going to be 1, 0. So I tend to read it as 10, even though it's not. It's 1, 0 base 2. So here, I'll put this up here. 1 plus 1 equals 2, which is 10, or 1, 0 base 2. Exactly. There are 1, 0 kinds of people. Exactly. And you guys are all gonna be ones? You understand binary? On off switch, remember? It's on. So if you do the same thing for multiplication, now we multiply the same way that we normally would. So 0 times 0 is of course 0. 0 times 1 is also 0. 1 times 0 is 0. The only time I'm both. Hey, how can that be? 1 times 1 is 1. So multiplication, I would argue, is a little bit easier. You don't have to keep in mind the 1, 0 base 2. Right? All right, so this is all we need, you say, or I say, I guess. So let's do an example. What if I have to find 1, 1 base 2 plus 1, 0, 1 base 2? Okay. Yeah, just sometimes you're on, sometimes you're off. So if we set this up just like we would kind of normally if you're doing arithmetic by hand, I know we don't really do that anymore, but now we kind of have to, right? So we've got 1, 1 base 2 plus 1, 0, 1 base 2. Oops, that should say 2. So now, right, what I'm going to do is I'm going to add, so 1 plus 1 makes 1, 0 base 2. So just like if we landed on 10 in normal arithmetic, we would write the 0 and carry the 1, right? And that's exactly what we're going to do. So write the 0, carry the 1. And I'll just emphasize here, since 1 plus 1 equals 2, which is 1, 0 base 2, okay, we write the 0 and carry the 1. That should say carry. So now, right, I've got 1 plus 1 plus 0, puts me at another 0, 1, or sorry, 1, 0. Carry the 1 again. So now I've got 1 plus 1 is 1, 0. Base 2, of course, because we're working in base 2. So now we have our answer that it's 1, 0, 0, 0, base 2. Let's do a multiplication example. So if I have the same 11, so 1, 1 base 2, oops, times 1, 0, 1 base 2, just like you would in multiplication, right? We set it up the exact same way, we're multiplying now. And when you're multiplying, right, you have to take, I'll set it up first here. So 1, 1 base 2 and 1, 0, 1 base 2, and we're multiplying. So what we have to do, right, is I have to take this one, multiply by this one, and then the lower one multiplied by the second or the first one, I guess. And it's hard because it's not a fraction, so I can't call them numerator, denominator, that type of stuff, right? But hopefully we remember doing multiplication by hand like this. And so if you have 1 times 1, that's 1. 1 times 1 is 1. Okay? And then 0 times 1 is 0. 0 times 1 is 0 again. And then 1 times 1, placing it under that 1. 1 times 1, oh, there we go. And then 1 times 1 again is 1. And then remember, you add these all up, or kind of smush them together in this case because it's going to be smushable. So this one gets brought down, 1, 1, 1, 1, base 2. So pretty fun. You got it. I just need to think of some numbers. How about, what's so hard about it? Figuring out, oh, thanks. Coming up with numbers. Thank you, Reid. A series of 1s and 0s. It's never been harder. Let's do 1, 0, 1, 0, base 2 times 1, 0, 1, 1, base 2. Thank you. So we've got 1, 0, 1, 0, base 2, times 1, 0, 1, 1, base 2. All right. So I'm going to work my way over. So the last digit in the bottom number just slowly gets multiplied over, right? And we write out that number below. So just like we did here, right? We start with our underneath the number that we start with, and then we move our way over. Okay? So 1 times 0, is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. Okay? So now I move on to this second one, right, from the right. And whatever my first result is goes underneath that number, right? And then I collapse them all up. So I get 1 times 0 is 0, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1. You want to really make sure that I didn't do a very good job of keeping things nice and lofty, but I'm trying to keep them all kind of stacked, right? I'm not doing a great job at it, but we can all work on stuff, right? Same with my repeated division, right? It just kind of flops over eventually. So now I go on to the 0 times 0, and I place the first one underneath that 0. So 0 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0, 0 times 1 is 0. Not bad. And then finally my 1, my first one, not from the left now, I place my first number underneath that 1. So 1 times 0 is 0, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1. Haha, just out of room here. All right, so now I collapse this all down by adding them together, keeping an eye for 1 plus 1, right, which I need to be careful with. Hey, this is a great example. So I have 0, 1 plus 0, 0 plus 1 plus 0 is 1, 1 plus 0 plus 0 plus 0 is still 1, 1 plus 0 plus 1 gives me 1, 0, right? So I have to put the first, hey, what happened here? the first 0 here, and then I carry the 1. 1 plus 0 is 1, and then 1. Oh yeah, where did I get that 0 from? Uh-oh. What have I done? 0, 1. What happened there? 1 plus 0 is 0. Classic. No bueno. Okay, I'm just gonna make sure that I did the rest of them properly. 0, good. 1, good. 1, good. 1, good. 2, carried. 1, 1. Okay, I'm ready to commit this. And it's the same that Riley has, so I'm happy. And of course, we're going to emphasize that this is base 2. Nice. I'm going to steal that one, put it in my notes. If I ever get to teach this again, we'll see. Okay. So let's see here. Let me just have a look. Okay. So how's that feel? All right, we had a little bit of addition in there as well. But as long as you remember these rules, and the only weird thing is that 1 plus 1 makes 10, or 1, 0, base 2, then you're kind of good. Okay. Any questions before we move on to the next section? Seeing none. So here we go. Let's talk about, so the last thing we're going to talk about is just kind of focusing on the relationship between binary, octal, and hexadecimal numeration systems and how we can move between them. Okay, so we'll call it octal and hexadecimal numbers. And conversion between bases, just in case you're having a look at your course outline. I know it's probably long gone by now, but or forgotten rather. But this is the section that's given in class. So here we go. So this part is not covered in the textbook. But this is all you'll have, so you'll be fine. So conversion between bases, methods, and algorithms. Okay. As you might have guessed, if you want to move from base 5 to base 3, for example, what you can do is you can go from base 5 to a decimal, so base 10, and then go from a decimal, so base 10 to base 3. So you can use kind of base 10 as a gateway drug, if you will. So base 10, that's what we kind of go through if we have to do conversions in general. There are some shortcuts going between binary and octal and binary and hexadecimal and vice versa. But of course, they're all relating to binary. So in general, when we convert between bases, convert between, and I'll specify between two two non-10 bases, if that makes sense. All right. We use the decimal, which is, remember, just the way of saying base 10. So the decimal base 10 as a gateway. So for example, if we have to convert 3464 base 7 to base 5, what would we do? You would convert 3464 base 7 into base 10 and then go from base 10 to base 5. Right? So what would we do? Right? Convert 3464 base 7 to base 10, then convert base 10 to base 5. So that's generally how you can move between any base, right? So we already know how to convert between bases. It's just got that extra step of going between base 10 and something else. So for example, if we have to actually do this problem, right, we've got 3464 base 7, and if I just kind of imagine here, I've got 7 to the power of 0, 7 to the power of 1. Hey, I should have written this out loftier, shouldn't I have, for my own sake? 3464 base 7. 7 to the power of 0, 7 to the power of 1, 7 to the power of 2, and 7 to the power of 3. Okay. Right, I'm working in base 7. I always start with 7 to the power of 0, to the power of 1, 2, 3, and so on and so forth if I need them. So this becomes 3 times 7 to the power of 3, plus 4 times 7 to the power of 2, plus 6 times 7 to the power of 1, plus 4 times 7 to the power of 0. Okay. Which is going to be 1029. I've got them kind of Martha Stewarted here, plus 42 plus 4. Which is going to be 1271 base 10. So now that we have it in base 10, we can convert it to base 5 just like we wanted to, right? So we can convert 1271 base 10 to base 5. Oops. I tried to write it out in words. You can use numbers if you want, but sometimes I find it gets confusing. So that's why I try to write it out in words, the numbers, so base 10, base 5, etc. But sometimes I forget. Okay, so again, I'm dealing with a page break here, so I'm going to put my 1271 right at the bottom of the page and just hope it works out. So 1271, and I'm converting to base 5, so I'm going to do repeated division by 5. So 1271 divided by 5, oops, 1271 divided by 5. puts me at 254.2, which, so what I'm gonna do is I'm gonna do 254 times 5 is 1270, which means I have a remainder of 1. Now 254, I'm gonna divide by 5, which is 50.8. So 50 times 5 is 250, which means I have a remainder of 4. If I divide 50 by 5, I get 10, with a remainder of 0, right? 10 times 5 is 50, which I've got 50 to deal with here, so remainder of 0. 5 goes into 10 twice, with a remainder of 0. 5 goes into 2 0 times, but the remainder here is whatever's left over, which is my 2. So I've managed to kind of have this sway here, but overall I'm feeling pretty good. So now what we can say is that 1271 base 10 is going to be 20041 base 5. So now I can write it out just kind of as a long thing. So therefore, 3464 base 7, and I'm going to include my my kind of gateway, my base 10 gateway. You don't have to, right? But I like to show off everything that I've done and worked on so far, right? So 1271 base 10 is 20041 base 5. Good. Moving between binary and octal and binary and hexadecimal, we do have some shortcuts that we can use. So we can absolutely just use base 10 as our gateway, but that could be kind of lengthy sometimes. So now I share with you the shortcuts. So the shortcuts here, when moving between, between binary and octal, which is base 8. Okay. Well, doesn't look like base at all. Base 8, and binary and hexadecimal, which is base 16, we have shortcuts. We have shortcuts which eliminate the need to move to base 10 before doing the final conversion. So which eliminate the need to convert to base 10 before the final conversion. Okay. And what you'll find is that they have pretty well the same layout. They follow the same idea and the same structure. So we'll start with moving between binary and octal, back and forth. Okay. So here, converting between binary and octal. And I'll underline it so that we have it if you're scrolling through. Okay. So the first thing that we need to remember is that if we're working in base 8, which is octal, then we have 8 symbols, right? So recall, octal, which is base 8, has 8 symbols, which I guess I shouldn't do colon, colon. In base 10, oh, I'll write 10. 0, 1, 2, 3, 4, 5, 6, 7, and I guess that's it. I was gonna keep going. No, 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 no. Just like my typo on the test. So base 10, we have oh, so here, these are also in base 8. But for us to easily think about it, I'm gonna first go from base 10, but these are also in base 8 because they're the first 8 digits. Cool, but good catch. So what we're gonna have is in binary, okay, 0 is going to be 0, 0, 0 base 2. And now because I've already written binary up here, I'm actually not going to write base 2 for all of these. My hand's cramping enough as it is. So you can go ahead and you can convert 1 to binary, 2 to binary. In fact, it's a really good exercise, right? I think you'll find that you will become really fast at converting to binary at these lower digits, right? Remember, the first slot is your 1s, the second slot is your 2s, and then you've got your 4s. Yeah. So we've got 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. So here, if we look at 3, for example, I've got 1 in the 1 spot and 1 in the 2 spot. So together it makes 3. 2 plus 1 is 3, right? So you can convert each of these back from base 2 to base 10, right? All right, I should. What's the harm? Hey, I could copy paste this. Right. But because we said binary up at the top, we don't have to do that, right? But it's just a good reminder. So then in octal, which is base 8, right, this is going to be 0 base 8, 1 base 8, right? Because we only listed the first or the 8 symbols of octal, it'll be the same as our base 10. 6 and 7. And how's this for cheating? Copy, paste. I think that's taking longer. 8. Well, because I want to be proper. Okay. So the shortcut, okay, notice that each of these, right, only have 3 digits, right? So we only need three digits here to make up an octal, right? So what we do is we take a binary number. So if we have to move from binary to octal, we use groups of 3. So to go from binary to octal, the first thing you're going to do, I'll call it A because otherwise it's a lot of numbers. You have to divide the binary digits into groups of 3. Divide or group, so divide the binary digits into groups of 3. And I'll underline the 3 digits. Starting from the decimal point. And I'll also say, okay, you have to add leading or trailing zeros if you don't have 3 digits, right? So add leading / trailing zeros, depending on which side of the decimal you're on. So add leading or trailing zeros if needed. The next thing you're going to do is you look at each of these groups of 3 and you convert them to base 8. Convert each group of 3 binary digits into 1 octal digit. Let's do an example. I'll try to keep the steps on here, but first I'll write it out. Convert 1 1 1 0 1 1 1 0 base 2 to base 8. Okay. So what we're going to do, right? So here we're going from binary and we want to go to octal, okay? And so what I'm going to do, so my decimal point would be here, and then I'm going to make groups of 3, right? So my decimal point in this case, because there is none, would be on the far right. So I'm going to write this out a little bit bigger, a little bit loftier. 1 1 0 1 1 1 0. Okay. And then I'm going to group these in groups of 3, moving from here, oops, from the very right, making groups of 3. Okay. And then I go on, and then here, I don't have a group of 3, but that's okay. I can replace 1 with 0 0 1. That's allowed. Nice. Good. So now, because we've already written out all our conversions, right, from binary into octal, right, now all I'm going to do is, if you have this handy, right, and it's pretty easy to generate, right, going just through base 10 numbers into base 8 numbers into binary. Okay, so this is easy to generate. Okay, and I encourage you to try doing it, right? I think you'll find that it's not bad at all. So then now all I need to do is find my 3 numbers in here and match them to the octal. Okay. So this becomes, oh, so 110 base 2 is 6 base 8. 101 is 5 base 8. 001 is 1 base 8. So what we get is that in total, and there's nothing fancy going on here, right? We're listing the numbers as they appear. 156. So it's 156, so 156 base 8. So that's kind of nice. You don't have to do kind of that long expanded version, right? Convert it to base 10 and then followed by repeated division by 8. That sounds nasty, right? So this is quite a shortcut. Let's do another one. If we have to convert 10.01 base 2 to octal. Okay. So now again, I'm going to write this out nice and lofty. 1010.01. And now I have a decimal to work with. That decimal translates into my base 8. Okay? And so this decimal is where I start, and that's where I move to the left and do my groupings of 3. So here, grouping of 3, and again, I have 0, 0. And moving to the right, from the decimal, right, I've got 0, 1, 0. Okay. So now I can convert these. So 0, 0, 1 is 1 base 8, 0, 1, 0 is 2 base 8, and 0, 1, 0 again is 2. So what we get is 12.2, and what I'm going to do is you can write 8 base 8 or oct if you want, octal. Base 8. So you create groups of 3 even if you don't have any, right? So here, if you're moving to the, so if you're on the left of the decimal, then you add leading zeros. If you're to the right of the decimal, you add trailing zeros. So it depends on where you are on the decimal. Okay. To convert from octal to binary, right? We do the same thing, but we just move backwards, right? And so I know that 2 is 0, 1, 0, right? And that's all I do. To convert from octal to binary, convert each octal to a 3-digit binary. And then you just put them all together, smush them all together as a single binary. Combine as a single binary. Let's do an example. Oops, 71 base 8 to binary. So now I have 7 base 8, and I can go back to my little table here. 7 base 8 I can replace with 1, 1, 1 base 2. And then 1 I can replace with 0, 0, 1 base 2. So here, 7, 1 I can replace with 1 I can replace with 0, 0, 1 base 2. And 7 can be replaced with 1, 1, 1 base 2. So what I get is 1, 1, 1, 0, 0, 1 base 2. So for these shortcuts, you're not adding or subtracting or anything, you're just putting whatever you get together, right? Depending on if you're going from octal to binary or vice versa. Well, regardless of if you're going from octal to binary or vice versa. That's what I should have said. Yeah, the old smudge and squish. Ooh. Good. How about, and I'll keep it on the same page here. So I'll write it like that. We'll do another example. What if we want to do something like 327 oct to binary? Smudge and squish. Sounds German. Was ist das? So 3, right? 3 is going to be replaced with 0, 1, 1. Okay? And so what I'm going to do is I'm just going to write it out. Oh, rats. 0, 1, 1 base 2. 2 is 0, 1, 0 base 2. And which we already established when we were adding, right? Call it 10, but 1, 0. And 7 is 1, 1, 1 base 2. So what I get is 327 octal is 0, 1, 1, right? We just read it across here, even though I made it kind of fun wave. 0, 1, 1. 0, 1, 0, 1, 1, 1, base 2. Ta-da! Shortcuts. No, you don't need this one. There's no, obviously you can drop it. But it might be hard to retrace your work if you leave it out. Yeah, so for, like you said, for grouping purposes, thanks Riley, for grouping purposes, I would keep the leading 0. It's not doing anything. So you can drop it if you don't want it, but if you're going back to check your work, right, it's kind of nice to have it, but if you remember that you were fancy, then that's great. Okay. Hexadecimal is very, very similar. The only difference is that we're grouping by 4s instead. I shouldn't say the only difference, but the main difference is that we group by 4s. Hexadecimal, right, is base 16. So we run into this problem of in base 10, we only have 9, or we have 10 digits, right, 0 through 9, and then we run out. So then we have to generate other symbols that we can use up to 15, which would be the highest, the largest symbol in hexadecimal. Hexadecimal. So here, now we're going to be converting between binary and hexadecimal. So just remember that hexadecimal is base 16. Which means we have to have 16 symbols. How about I just ditch these brackets and just keep writing? Hexadecimal is base 16, which means we need 16 symbols. And maybe I should make a little space here. That might look better. Okay, so we have 16 symbols. So let's start, and then we'll just kind of go from there. So if we have 0, 1, 2, and I'm going to move these over a bit because I'm going to make 2 columns so that they stay on the same page here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, this is in base 10. Okay. Just so we kind of keep track, right? But what happens is we run out of symbols here because now we're recycling our old symbols, right? 1 and 0. So what we do is we say that this is going to be A, B, C, D, E, and finally F. Okay. In hexadecimal. Okay. So otherwise, all these other ones, 0 through 9, are the exact same as they have been, right? But now we have A, B, C, D, E, and F to get us all the way through 15, which gives us 16 symbols, right? Because we have 0 making a mess. But also saving our bacon, so pretty good. All right, so if we work backwards here, if I had to write 15 in binary, right? 15 in binary. Hey, they use hexadecimal in Pokemon Go? Cool. I never played Pokemon of any sort. But I do know how to get Pikachu on the bus. You Pokemon. Oh. So Pokemon didn't teach you Hex. You taught yourself Hex. Why don't you shower with the Pokemon? Because he might Pikachu. I used to work at a daycare when Pokemon was big, so. That's true, that's true. So getting back to Hex, 15, if we're moving from 15 base 10 to binary, what we have is we would have to have 1, 1, 1, 1, base 2, okay? Because it's 1 times 2 to the power of 0, that's 1, plus 1 times 2 to the power of 1, so 1 plus 2 plus 4 plus 8. 8 plus 4 plus 2 plus 1, 15. Okay. So I'm just going to give you these, but I want you to go through and just figure out that you know how to find these binary numbers, right? So I'm just going to give them to you, but you know how to find these, right? And it's a really good exercise to just be able to set up. I know it feels like a lot, 16, but they're going to come very quickly. Okay? So E in hex is going to be the same as 1, 1, 1, 0 base 2. D is 1, 1, 0, 1 base 2. C is 1, 1, 0, 0 base 2. 1, 0, 1, 1 base 2. 1, 0, 1, 0 base 2 is 10, or A. Okay. Notice that because these required 4 digits, now we're going to force all these other ones to have 4 digits as well. We just add leading zeros, right? So 9 is 0, 1, 0, 1 base 2. 8 is 1, 0, 0, 0 base 2, right? 1 times 2 to the power of 3. 7, 0, 1, 1, 1 base 2. Notice that I'm just recycling now from here on out. I'm recycling. 9 is... Yes, it is. Why did I have... Agreed. 8 plus 1. Thank you. You guys are on it. Hey, how come it's so dark in here? You see me? I don't see the screen anyways. Sometimes I have to move around. Okay. Hopefully that's the only one. Yeah, 4:30 for me. Yeah, it's nighttime, I guess. Weird. It is actually getting dark. So close. Okay, so hopefully I haven't mucked up any others. In fact, before I forget, why did I write there? All right, the other ones, so from here on out, right, these are going to be the exact same as what we had before, right, just with a leading 0 in front of everything. Right? So if you set up this hexadecimal table, you'll also have the octal table if you just drop the leading 0. So we have 0, 1, 1, 0 base 2, and this is binary as well, of course. 0, 1, 0, 1 base 2, 0, 1, 0, 0 base 2, 0, 0, 1, 1 base 2, oops. 0, 0, 1, 0 base 2, 0, 0, 0, 1 base 2, and finally 0, 0, 0, 0 base 2. keeping in mind that for hex we use A, B, C, D, E, F if we need something larger than 9, right? And then, but from there on out, noticing that we're grouping by 4 here instead of 3, that's the only difference. So now moving between binary and hex is going to be relatively easy. We group by 4s, and then moving from hex to binary, of course, works the exact same way as octal. So to go from hexadecimal to binary, okay, the first thing you have to do is you have to divide the binary digits, oh yeah, from hexadecimal to binary. Hey, this is going from binary to hexadecimal. What the heck? That's what I want to say. To go from binary to a hexadecimal, that makes more sense. Divide the binary digits into groups of 4. Starting from the decimal point. Okay. And of course, again, add leading or trailing zeros as needed. Add leading / trailing zeros as needed. Then convert each group of 4 binary digits into its hex. So convert each group of 4 digits into 1 hexadecimal digit. Okay, good. Let's do an example. If we have 1101 base 2 to base 16. Okay. So again, I start from my decimal, which is just the far right in this case, and now I move, because I'm going to base 16, which is the hexadecimal, I move in groups of 4. So here I've got 4, and then I need to put on a leading 0. But now all I have to do is I have to match 0110 to its hexadecimal. And if I look at the table we just made, 0110 is 6. And 1101 is D. So we're at 6D. So we have 01101101 base 2 is 6D. I wrote oct, but I meant hex, just for a nice shorthand. Okay. Same idea, right? If I have some hexadecimal, I can just convert it to binary using the same kind of roadmap that we developed, that table. So to go from hexadecimal, now we're actually going from hexadecimal to binary. first thing you have to do is convert each hexadecimal to a 4-digit binary. Convert each hexadecimal to a 4-digit binary. And then the second part is combine as a single binary, just like we did before. Combine as a single binary. Let's do an example. If I've got C45 as a hexadecimal, all I do is I write out C and then 4 and then 5 in binary. So C is 1, 1, 0, 0, 4 is 0, 1, 0, 0, and 5 is 0, 1, 0, 1, and this is in base 2. So here, C, 4, 5. We can even have something weird, maybe, like 279.D2 as a hexadecimal. Remembering that the decimal just kind of, it stays and it translates to whatever base that you're working in, right? So it's just kind of a holding point. Okay, and so 2 becomes, and I'll just give them to you. How come this one has 4 numbers? Maybe I won't just give them to you. 0, 0, 1, 0 is 2. Okay. 7, I'm just going to steal them from here. 0, 1, 1, 1. 9. You guys fixed me up. It is 1, 0, 0, 1. Point D, which is 1, 1, 0, 1. And 2 is 0, 0, 0, 0, 0, 1, 0. Wrote a little too lofty there. 2, 7, 9, D, 2. And of course it's base 2. So I'm gonna just move this over a little bit. Okay. So what I want to do is, so that's the end of the concepts. I've got a couple of examples that I have up my sleeve here. So I'll write them out and we'll work through them. So I'll write them out, you can start working on them, and then we'll work through them, and whatever we don't finish, we'll just use as review for next day. Sound good? Cool. So examples here. 1, convert to octal. A, B, C. A is 1, 0, 0, 1, 0, 1, 1, 1. Base 2. These are all going to be base 2. B is 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. C is going to be 1011.01101 base 2. 2, convert to binary, 4, 5, base 8. Oops. 245.34. I'll use base oct this time. It's the same, right? Octal, base 8. 3, convert to hexadecimal. Oops. I always want to combine my words. If it ended on the same letter that the next word starts with, my writing just wants to combine them. I don't know what it is. Convert to hexadecimal. 100101111 base 2. 111011110111 2. C 1011.01101 base 2. And finally, convert to binary. 4C1 hex and AC hex. Okay. So like I said, we'll work through these, and whatever we don't get through, we'll use for review next day. I'll move these down a little bit, keep them for later. Okay, so to convert to octal, right, we move in groups of 3. And so moving from the very right, we group these in 3s. 1, 2, and add a leading or a trailing 0 if needed. Okay. And then what I can do is I can refer to the table that we made up, right? Where 111, I remember is 7, right? Because that's the largest number that I can have in base 8. 0, 1, 0, well, that's, let's see here. 1 times 2 to the power of 1 puts me at 2. 0, 1, 0 is 2 again. So we get 2, 2, 7, base 8 or oct. Okay. B. Oh, I had it down here, didn't I? Ooh. So again, moving from, I don't see a decimal here, so I'm going to move from the very right and move in groups of 3. And so I've got 1, 1, 1. I don't know, I find it easier to move from the left to the right, but then you have to count out 3 before you do, but that's okay. All right, so this first one was 7. 1, 1, 0 is 4 plus 2 is 6. 4 plus 1 is 5. And 2 plus 1 is 3. I'm just checking 3, 5, 6, 7. Yeah. Now I've got a decimal, right? So my groups of 3 move out from the decimal. Right? On either side, adding leading and trailing zeros as needed. So now 0, 0, 1 is just 1. 0, 1, 1, 2 plus 1 is 3. 0, 1, 1 is 3 again. 0, 1, 0 is 2. So this becomes, and remember the decimal translates down, right? So we get 13.32 base 8 or oct. Okay. Let's convert these to binary, and then we'll leave 3 and 4 for review next day. So 4, 5, base 8, just reading them as they come here, 4 base 8 is the same as 1, 0, 0, and maybe I should write them like this. 1, 0, 0 base 2, and 5 is 1, 1, 0 base 2. 1, 0, 1 base 2. What was I thinking? 4 plus 1, not 4 plus 2. So 1, 0, 0, 1, 0, 1 base 2. Oh, let's keep that same color. All right. It's almost over. You don't want to miss the finale. Just 5 more minutes. All right. 2 is 0, 1, 0. We kind of know that one, right? 2 makes 10, 1, 0. 4 is 1, 0, 0. 5 is 1, 0, 1, which I just stepped in. 3 is 0, 1, 1. And 4 is, I ran out of room. Maybe I should keep it down here. 4 is 1, 0, 0. So putting it all together, I get a really long binary number, right? But that's okay. 1, 0, game over. 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, base 2. Yeah. No snoozing for Zach. All right. So I'll leave the 3 and 4 for you guys to, hey, don't forget the decimal point. What was I thinking? Put it here and put her there. Thank you, Reid. All right, crisis averted and class dismissed. Any questions? Bye guys, see you on Wednesday.